All right. Well, despite all of the magnetic personalities in the audience, circumstellar disks do form, and I think we're going to focus on that this session. We'll have two talks before the coffee break and then 2 talks afterwards. And our first presentation is by Dmitry Semenov, and he's going to tell us about millimeter observations and modeling of planet-forming disks.
Do you hear me well? OK. Good morning, everyone. I hope that, unlike me, you're already awake. I still need a few minutes to do it myself. Today, I'm going to tell you a little bit about our recent progress in understanding the physics and chemistry of protoplanetary disks since the last Protostars and Planets VI meeting, like 7 years ago. And here's the team with which I prepared the slides and also written the chapter. And main focus of my lecture will be millimeter observations and modeling. First of all, I show you the outline of my talk. Being the first in this session, I will spend just 2 slides to present you the importance of the topic. So why we care about chemistry, why we care about protoplanetary disks. And then I show you the first results of the first limited specially resolved surveys of chemistry in disks. And then I show you the modern models of disk physics we developed over the last years. And then I will continue with observational results, so how we can use chemistry and molecular lines to study various aspects of this physics. After that, I will present you the new advances in terms of theoretical modeling of disk chemistry and tell you about the chemical composition of outer disks across various stars, and show you the predictions for Alma and the first Alma results, which are very, very exciting, at least to my taste. So our motivations to study disks comes from the fact that this is exactly the stage where the star is already born, but planetary system is not yet there, and it is being formed. So by studying this phase of the evolution, one can answer the question about the planet formation processes, but also probably discern the initial conditions of the planet formation. So we hope to understand better, by studying disks, to understand better the primordial atmospheres of the freshly formed planets. And with regard to the solar system, we want to understand better the composition of primitive bodies like comets and meteorites, and eventually also answer the question, what kind of organics was there? Were there life-building blocks already available in this stage? And the molecules are very useful probes of physics. My feeling is that whenever I say the word chemistry, it freaks out many of my astronomical colleagues. So please remember that for us, actually, the chemistry often means that we use chemistry or molecular lines just to study physics. And then kinematics, and then we can say, if we have enough detections in an object, we can say something about the chemical composition. So it's more like a cherry on top of a pie. It's fine to have it, but the pie is tasty without it. So on this slide, I show you the scheme of a disk. And here I want to emphasize you that it's a tricky business to study them both observationally and theoretically. First of all, they have a complex structure. So there is the freshly formed star. We see the accretion funnels from the dust-free inner region. Then we see the temperature drops and the dust appears. And so this is dust-rich zone. And dust is still tiny, so it has possibly mostly submicron-sized radii. It's still enough of dust there to shield the disk such that it has a very strong gradient of temperature and densities as well. In terms of chemistry, it translates to the following fact. So we have very cold outer midplane, where the many molecules are frozen out, and we have very rich ice chemistry happening on the tops of the dust grains. This is this blue zone. A bit above that layer, or that zone, midplane zone, lies a molecular layer, where the gas-grain interactions are very efficient, and where a bit of UV radiation from the star can penetrate and drive also very active gas phase chemistry. So this is this yellow layer. It's actually the region from which most of the molecular lines comes from, the rotational lines of simple and complex molecules. And then at top, we have a very highly irradiated, hot disk atmosphere, which is mostly populated by simple atomic species or atomic ions. the picture is complicated by the fact that the disks do evolve. So there is a viscous accretion, so we have a transport of matter inward, and the fraction of matter transports the angular momentum outward, so it works in both ways. We also have turbulence, and therefore we have turbulent transport in all directions. And then we also have the dust evolution. So eventually dust will grow and form planetesimals. And of course, it also changes the transparency of disk to the stellar and interstellar radiation, and it changes its physical structure. So I'd like to remember that disks are relatively compact objects, a few hundredths of a U in size. They have not that much mass left, a few % of the stellar mass, and they don't live very long, even on geological scales, such as a few million years. Therefore, they are very hard targets to observe them, especially in molecular lines. On the modeling side, of course, because of this complexity of the processes, these are hard objects to model. They have gradients of physical conditions, dust evolution, dynamics, high energy radiation. That makes it very difficult. OK, that's it with the introduction. Now I would like to show you what we achieved in terms of chemistry studies. And the first big success since the last PP5 meeting, I think, is that the first limited specially resolved surveys became available, thanks due to the efforts of two big groups. The first one called Chemistry in Disk Collaboration, and this collaboration brought together the scientists from Europe, USA, and Taiwan. And these guys used the plateau de Beer interferometer and the RM centimeter antenna mainly to study the chemistry in disks. And another big collaboration is Disks Imaging Survey of Chemistry with SMA, so Disks collaboration, mainly from the United States, who use the submillimeter array to do the studies. Well, so far we've been able to observe about a dozen of large nearby disks, and the names are given here, that encompass stars of various spectral types from T Tauri to Herbig AE stars, and they have different properties. The key point here is that lines are very weak. They are of order of maybe at most 1 Jansky, usually weaker. And just to detect one line, one needs to have a few hours with a modern radio interferometric facility like Plateau de Beer. And these facilities are very highly competitive, so it was quite hard to get enough time to detect a handful of molecules. Well, we managed to succeed. It took really several years just to study these several disks. Well, the first thing you do when you observe a number of objects is just to compare what you see. And on the next slide, I show you the very nice picture from the Karen Obrick's paper that just shows the integrated line intensities across disks from M up to the A-type stars, from DM tau to MWC 480. What is shown here are the lines of CO, HCO+, DCO+, and 2H+, H2CO, HCN, DCN, and CN molecules. Well, the first thing you see that the spectra are quite noisy. This is the problem of detection. The CO lines are very strong and visible more or less in all of the disks. Then HCO+ are usually always strong enough to be detected. Well, not in the case of CQ tau. But you see that other lines are not detected in more luminous stars. And this is indeed so. From this limited statistic, we've seen that Herbig AE star disks tend to have less molecular lines visible than T Tauri stars. And why it is so, I will explain later during my presentation. OK, the next step, then, to make sense out of all this data is to use models. And the first models which we need to have at our hands is the model of disk physical conditions. And during the last year, there was enormous progress with that respect. The next slide, I just want you to show one of the current results. So the first model of that kind, which we called thermochemical models, because they take into account detailed treatment of the gas heating, which then requires somewhat a chemical modeling, at least with respect to key molecular coolants of the gas. So the first models of that kind have been developed by Inga Kamp and then Peter Wojtke, which is called this Prodemo model. And here I show you the results which obtained with our recent ANDIS model that includes also the grain evolution. What is shown here is the dust temperature, gas temperature, and the density distributions in a dm tau-like disk. Here is the height over radius ratio shown here. The star is somewhere here, and this is the radial distance from 0.5 AU up to 500 AU. What you can immediately see, the color coding is like that. The red in my plots is always something which have a high value, and the darkish color something which has low value. What you see here is the cold midplane and very highly radiated atmosphere. And it's clear, I hope you clearly see that gas actually in these upper layers becomes much more hotter than the dust. And that from the point of view of density structure, we have the exponential drop in the vertical direction, but we also have the radial gradient. And this is the structure that corresponds to a theta rise system, that the effective temperature is about 4,000 Kelvin. We still have quite substantial amount of X-rays, which basically resembles our solar-like flares, but magnitude of 1,000 times higher. And then we also have UV radiation coming from the star. Then if we would calculate the same structure for Herbig disks, it would look similar but a bit differently, in the sense that the stars are hotter, they have a bit less X-ray luminosities because they don't have convective atmospheres, but they produce much more UV radiation. That makes the disks hotter. Here I again show you the temperature of the gas and density distribution, and this is from, this yellowish color is 10,000 Kelvin, this darkish color here is about 20 Kelvin. That's from the paper of Nomura-san. And what is important here is that, first of all, it's, well, I haven't shown you here the dust temperature, but it looks a bit like on the previous plots. So again, the gas and dust temperatures in the upper layers are not the same, and the important point that Herbig disks are warmer. Here we have the lowest temperature of about 14 Kelvin, and here the lowest temperature is about 20-something Kelvin. The next question, if these models are feasible. And it was actually tested later. This is the paper by Vincent P from 2007, where they used various CO isotopologue lines to probe the vertical temperature gradient in several disks. What is shown here is the disk temperature at 100 AU from 0 to 100 Kelvin. And this is the effective temperature of the central star, from T Tauri star of 4,000 Kelvin up to AB Auriga, which is 10,000 Kelvin, this Herbig region. This colored lines, this red line is 12 CO221 line, which is optically thick and which traces the temperature in very upper layers of the disk. Then the yellowish line, the greenish line is 13 CO221 line that has less optical depth, and it stems from a bit more deeper layers, intermediate layers in the disk. And this blue line is for 13 CO120 line, the line that is excited somewhere around the midplane regions. And from the modeling point of view, you would expect that the temperatures recorded in this line should be lower than the temperature recorded in this 12 CO line. And this is exactly what is seen here. For dm tau, we have this progressively high temperatures from blue to green to red detections. And the lowest temperature is quite low, it's below. So here is 20 Kelvin, 10 Kelvin, so it's from 10 to 30 Kelvin. But important factor also is that we have the temperature rise. So we have the same vertical gradient of temperature in the Herbig systems, but the temperatures are higher. So the minimum temperature here will be of the order of 20-something Kelvin. So indeed, as we've seen in the previous slide from the modeling point of view, but as well as from observational results, it seems that the Herbig disks indeed are warmer. But there is one example of LKCA 15 here where all three measurements are at the same temperature. So in these disks, apparently, we don't have a vertical temperature gradient, and we don't understand why it is so. And actually, this disk has a large inner hole, so it's a transitional disk. And I hope that Catherine Espaliat later will talk more about the transitional disks and their structure that may be related to that fact. Well, the first global quantity which is easy to constrain from observations is the temperature, because it's basically proportional to some extent to the brightness temperature of CO lines. The next important quantity is the density and the total disk mass. And this quantity is much harder to get because H2, as we know, does not have dipole moment, so it doesn't emit when it's cold and cannot be observed easily. Then, on the other hand, the dust emissivities at long wavelengths are quite uncertain, so it's hard to convert the dust emissivities to the total gas mass, because we also don't know well the dust-to-gas mass ratio. People therefore relied on the other molecules as a tracer of disk mass. And one of the exciting discoveries made with Herschel, it's actually the paper by Ted Bergen and the Wish team, it's the discovery of HD line. So this is the hydrogen data rate molecule. Unlike H2, it has a weak dipole moment. Therefore, the pure rotation lines can be detected. And this is the line detected, HD 120, the ground state line, with the relatively high signal-to-noise of 9. And that allows a direct probe of the H2 and the total gas mass, because from chemical point of view, the ratio of HD to H2 is rather constant. It's not very much sensitive to temperature factors. The guys that then analyzed the spectra here, they came to the conclusion that despite being quite old, so it's between 3 to 10 million years old, the TW hydro disk is still quite massive, so it has a mass at minimum of 0.05 solar masses. So it is capable of forming planetary systems much like our own. Unfortunately, you know that the Herschel is gone. We don't, and it's kind of a unique measurement to some extent. But with Alma, we hope to probe many, many different molecular emissions from the disk. And each of these molecules would probably come from different disk regions. But using this as a proxy for the somewhat disk gas mass at different locations, we hope to then to be able to get the total density structure. So now I'm switching to another properties, physical properties that you can study with molecular lines. That's the kinematics. On this plot, I show you the velocity structure of a rotating disk. So because of the Keplerian shear, and these black things here, these are the 3 different velocities at which you measure the emission. Because of the Keplerian shear, if we look into the specific velocity, we don't image the entire disk. We image just a fraction of its surface, like here or here or here. And for example, if we go from the systemic velocity into higher or lower frequencies, we can actually sample the gas that is closer to the central region, even if we don't resolve it. So that's the power of molecular line observations. We can probe without resolving the structures quite close to the star. But these regions, the width of these regions depends on the local line width, which is determined by the thermal broadening and the turbulence. So this is the total line width. So from observational point of view, one can try to determine it. But for that, one has to know the disk inclination, which is usually relatively straightforward to get. Then the gas temperature, which we may get, as I showed you before, from CO lines. And then we have to know rotation. Usually it's Keplerian law, so it's also known. And then you can easily estimate the contribution, if you measure this from the observation, the line broadening here, you can get an idea about the turbulence. As you can see, thermal broadening term depends inversely on the mass. So it's favorable to get to use the heaviest species. For example, CS is one of the molecules that is detected in disks and can be employed. And the first study of this kind was made by Meredith Hughes and her team, where they used SMA to detect CO322 line in HD 163296 disk. So they use CO because it provides very high signal to noise, and so you can map also the line wings reliably. And they use different models to feed the data, and they came to the conclusion that models with turbulence included feeds the data better than the models without turbulence. So you see that's no turbulence, this is black line, and this red and blue line, these are the disk models with turbulence. So they came to the conclusion that in these disks, there is a non-thermal component, likely the turbulence of the order of 0.4 kilometers per second, which corresponds to 0.4 Mach, so it's subsonic turbulence as expected. Another study of similar study was a study by Stefan Gil using the CS data with plateau from DM tau, where they use a parametric model with a CS layer and fitted the data. And here what is shown is the non-thermal Vis as a function of temperature of the molecule. And the different lines here correspond to different temperature profiles. On the bottom panel, the observed flux density and the model flux densities are compared. So this gray box is these observations within the uncertainties. And again, these lines are different models. So from observation point of view, the low temperature CS is favored. This corresponds to the non-thermal light phase of the order of 0.1 kilometer per second. The important point here is that this turbulent Vis only weakly depends on the temperature. And again, this best fit value corresponds to about 0.4 Mach numbers. The important finding of this study was that to fit the data, they had to locate CS molecules at 1 pressure scale height. So they tried models with CS located from the midplane up to the atmosphere, but the best fit model required CS to be above the midplane. So that was one of the first indications that molecular layers, as I shown on one of the very first slides, may indeed be inherent part of the disks. Well, now we'll be slowly transiting to the chemistry results, which are more difficult to explain. On the next slide, I show you the plot from Vincent P. paper from 2007. It's a busy plot I try to explain you. So basically, it shows the radially resolved temperature profile as measured at 12 CO2 to 1, 13 CO2 to 1, and 13 CO1 to 0 lines, and the respective column densities. So the measurements are these black lines, and the red lines show the signal to noise. So to get these fits, they had to use the parametric modeling and chi-square fitting. And so they had to assume the outer size of the disk, the inner size, the inclination, where the molecules are located, the temperature profile, the density profiles, and so on. But whereas from the chemical modeling point of view, the column densities are somewhat like we expect. The temperatures are unusually low. If you can see, it's about 10 Kelvin. And CO molecules want to freeze out whenever temperature drops below 20 Kelvin. So there was an interesting result that apparently there are some cold gases in these disks. And later it was found also that it's not only for CO, but also for HCO plus, CN, C2H, and CS. They all want to be located in very cold disk regions where they have to be frozen out, but they're still somehow in the gas phase. And we don't understand why it is so. What Alma will bring us here is that will allow us to have much more parametric models. For example, if you go and read these classical Pringle papers on the evolution of viscous accretion disks, actually the density profiles are not power laws. They are more like power laws with exponential h in the end. And for example, with Alma, we will be able to parameterize the density profile, not like with one single power law, but with a number of power laws, and hopefully see if it's just a power law or indeed a power law with the tapered h. So another interesting point is to compare the chemical composition in different environments. So we know that before the disk stage, there's the molecular cloud stage. It's important to see what are the chemical differences between these two stages, because it may tell us something about the processes which are involved in there. So here's, again, the picture or diagram from our recent review that we've written with Thomas that shows in logarithm the abundances with relative of H2 for a number of molecules measured in DM tau disks, which is these red bars, and TMC1C. So this is a molecular cloud which is well studied in Taurus molecular complex. And what you see here is that for all of the molecules, the abundances of gaseous molecules in the TMC1, so in pre-stellar core stage, are much higher than those measured in disks. So the observers call this depletion. So why it is so? The current idea is that it is because the combined effect of freeze out in the colder disk midplane regions and more intense UV dissociation of the molecules in the upper layers because of the central star. And later I show you another indications for that. Here we see the recent additions. This is DCO plus DCN measurements, which are also different in disk of DM tau and TMC1. But here we have a less idea about why they're seen there. Is it the fossils of the previous very cold ISM phase where the DM fractionation is very active? So you can see this here. Or they can be in situ produced in a bit warmer disks, therefore they have lower concentrations. So please see a talk of Paulo Castillo later. The next exercise we did, we compared the chemistry in one of the Herbig disks and the chemistry in one of the T-Tau disks. As you remember from the physical structure plots, the thermal structure is different, also the radiation intensities are different. And here I show you the table from one of our papers that shows different species and their relative abundances with respect to certain CO. And H2 here is just the value that is converted from the dust emissivity, so it's subject to high uncertainties. Therefore, we decided, okay, let's scale everything to certain CO because we measure it directly. So, and then you see here HCO plus, HCN, CS, C2H, and formaldehyde. And if you compare the AB Auriga and DM tau disks, so you see that these values here are lower than the values in DM tau disk. And later it was found also by the Karen Erberg and her collaborators in other cases. There are currently two ideas why there could be possibly this chemical differentiation taking place. The first idea is that Herbig A disks are warmer. If you remember the plot, they are warmer than maybe 20, 25 Kelvin. And that implies that CO cannot freeze out on dust grain surfaces. Therefore, there is no CO grain surface chemistry which produces formaldehyde and methanol, and the complex molecules have less chance to be formed in AB Auriga disk. That is one explanation why it could be molecularly poor compared to DM tau disk. Our idea is different, is that the AB Auriga has a low X-ray luminosities. And what X-rays do, they do a very important job. They are able to ionize helium, which has a high ionization potential. And the ionized helium then is able to destroy CO. And CO is a measure reservoir that locks almost entire carbon budget and half of the oxygen. Another half of the oxygen is in water molecule. So the ionized helium breaks up CO and brings elemental carbon and oxygen back to the gas phase where you can reform other species other than CO. And so our idea is that since the X-ray luminosity of AB Auriga is lower, that therefore we produce less of other carbon and oxygen-bearing species from CO. Right. Another very important finding with respect to molecule that astrobiologists love and dream about, and which brings nightmare to modelers who wants to model the line radiative transfers, and I'm talking about water. Another very important study was the first detection of ortho and para and ortho water in TW Haider disks with Herschel. It's a Wish collaboration. It's a very nice paper by Michael Hoger-Heide that shows, as you can see, quite strong signal. Water behaves a bit differently in disks compared to CO. Water is frozen when the temperatures are below, let's say, 100, 130 Kelvin. And there was one of the earlier paper by Karsten Dominic where they showed that, in fact, we do still expect to see gaseous water in disks, but not because of the thermal evaporation of water ice, but because of the photodesorption. So the UV photons can penetrate, and they just can remove some of the water ice in the atmosphere. Karen Oberg did a very nice measurements with regard to efficiency of this process. So from the laboratory point of view, it's very well known. But unfortunately, if you put all these numbers into the models, we are getting much too many cold water vapor than was observed. When this paper appeared, I came back to literature and checked all the theoretical predictions from all the astrochemical disk models, and they all were much too high column densities of water by a factor of at least 10 or 100 usually. And so the authors of this paper, they proposed two different scenarios why we could see so little water actually in this TW header disk. The first one is that somehow water ice is preferably located in the big icy grains that are able then to sediment to the midplane region, therefore they escape the photoevaporation. And the smaller grains which sitting high in the disks and from which the ice could have been photodesorbed have less or no water ice at all. Another idea is that these icy grains are somehow transported to the inner regions, and therefore the signal is less, and the lines may be actually optically thick. So these are two interesting indications that indeed these dynamical processes or grain evolution processes can be important for chemistry. This is observational indication, not just a theory. From the theoretical point of view, I can show you in the next couple of slides the predictions. Yeah. The first one is the modeling of chemistry with grain growth. There are a number of models made over the last years. Basically shows you the three models and distribution of CO in the disks from 10 to 500 AU, and this is the vertical scale over radius ratio. This is CO molecule. The red is the molecular layer of CO. It is frozen in the midplane region. And it has more or less the same structure for all these three models. And the first model is this uniform dust of 1 micrometer size. The middle model is the same uniform dust, but submicron sized. And here's the model with the evolution. So the large grains are sedimented here, and there are small grains over there. While the overall appearance is the same, so we have molecular layer, but its location is different. The bigger grains in the midplane delays the freeze out, whereas less shielding by dust in the upper layers make the photodissociation more active. Therefore, the molecular layer shifts a bit closer to midplane and depletion zone shrinks. And a number of potentially observable tracers have been identified which should be sensitive to the grain growth. Another interesting finding was that actually Lyman alpha radiation may reach these very, very shielded regions. So there was nice work by Jeff Fogel and Tom Bittel that basically showed that due to the resonance scattering on hydrogen atoms, Lyman alpha photons can actually reach these very, very dark regions. So similar study is being done by Catherine Walsh, and here I show you again the distribution of water vapor in a disk from 0 to 300 AU with different maximum grain sizes from 10 microns to 1 millimeter and to 10 centimeters. So it's very, very huge grains. What we see here is the hot layer of water in the inner region in the atmosphere. Then this darkish color is the depletion zone of water. And here's this water molecular layer somewhat here. What you see here is that with the grain growth, the shielding again becomes less effective, and the water is getting more and more intensively photodissociated, so this zone of hot water vapor shrinks. On the other hand, the depletion zone shrinks as well, but the molecular layer becomes bigger. So more or less they came to the same conclusion as before. There were a number of models where the people studied the impact of dynamical transport on chemistry. And here I again show you the water distribution as on the previous slide, and two models without gas motions and with vertical transport of matter by mixing. What you see here again is abundant water vapor in the hot inner region where the water ice cannot exist, so water is in gas phase form. Here it is frozen in the midplane, and this is the water-rich layer produced by photodesorption. If you can compare both these models, the structure stays the same, but water is more abundant in the mixing model. And this is because more of the ingredient that form water through this slightly endothermic reaction, which has a barrier of about a couple of hundred kelvins. So the mixing brings more of H2 in this region and also OH, and allows more water to be formed. It's like, there's a cooking spot where the water could be cooked with this reaction, and the mixing just brings ingredient, and therefore the more water is being produced. So they also found a number of observational tracers of these processes beside the water. Well, we did a similar study. It's more or less the same plot as before. We have this height in the disk normalized to the pressure scale units, which observers love. And it's again shown the radial distance from 10 to 800 EU. In a DM tau-like disk, 3 models are shown without any gas motions, with slow and fast turbulent mixing. So it's in 2 dimensions. So the gas is mixed in this way. You again see for CO, for gaseous carbon monoxide, CO molecular layer and the depletion zone, but they look more or less the same here. On the other hand, for CO2 ice, in the laminar model, we have just a tiny region where it can be formed. And it can be formed, again, from the reaction that has a barrier. Therefore, it only forms in the warmer inner midplane region. However, if we, again, switch on mixing, we bring the constituents in this warm region and cook CO2 ice, which can be then transported in other regions. Therefore, we have huge enhancement in CO2 ice in the end. We also identified a number of observational tracers of the mixing, which should be a heavy species. And the key point is to remember is that sensitive species to transport are those that have chemical timescales which are longer than dynamical timescale. Usually it implies the species formed through the surface chemistry. Okay, I probably need a couple of more minutes to show the few of the Alma results. As you know, it is almost completed. This is one of the recent pictures. It will be comprised of 50 antennas, and then also the compact array here to get the missing short spacing flux done, and also single dish antennas. It has a very tiny resolution at 1 terahertz band, about 1 AU at 100 per sec. It will allow also to observe a very wide frequency range, within 1 millimeter to far infrared range. It will produce gains in line sensitivity by at least factor of 10 and as well as resolution, and it will lead to the Alma revolution. So first of all, we will be able to detect organic lines in disks like TW Hydra. So these are the modeling done by Catherine Walsh that shows the intensities of the lines of formaldehyde and methanol, and actually the noises at these bands are of this level. So some of the stronger lines will be easily detected. So the next study was our study of the visualization of molecular layers. Here, what I show you is the different velocity channels for HCO plus 423 emission calculated with 2 models. One is the molecular layer of HCO plus, and another with uniform distribution of HCO plus. And they look quite differently. We put then one of the channels where they differ most into the Alma simulator. And it turns out that at sub-arc-second resolution, you will be able to see the difference in these tiny features. It was purely theoretical paper which has been written and forgotten, but in last months, they found with Alma scientification data exactly quite similar structure in CO molecule for HD 163296. And actually, they cited the paper. That could be one of the first direct evidence for the presence of molecular layers in disks. So these are basically directly visible. Of course, Alma will bring a lot of new molecules. One of those is a small cyclic hydrocarbon observed again in the same disk. And it also shows that the chemistry of this particular molecule can be related to CO chemistry. And then we also have a recent data which we got in March from Cycle 0 that shows angular resolved chemistry in CN. So all these substructures are real. So you can see for the first time very, very rich spectra with a lot of things in there. Okay, the conclusions. Well, I hope that you may remember from my presentation that during the last few years, we made a nice progress in understanding the chemistry and physics in disks, and we made the first limited surveys of disk chemistry and poorly especially resolved though. We gained the first information about temperature, density, and turbulence in these disks. We start seeing for the first time that there could be chemical differentiation between T-Tauri and Herbig-Ae disks. And there are a lot of very advanced models that have been developed which can be applied to analyze very nice Alma results. So, you know, it reminds me a bit the history of the discovery of the New World. What we have now is like a map that shows very vaguely and crudely a far distant land, just maybe a shoreline, but we don't know how exactly it looks like and what it is there. And the incredible Alma machine will allow us for the first time to reach this exoterra incognita and to gain the complete understanding of the chemistry and physics in protoplanetary disks. Thank you very much.
We have time for a few questions, and I just want to remind the audience that there are microphones set up in each of the aisles, both on the ground floor as well as in the terrace. So let's begin with Peter.
Peter Voigtke, St. Andrews University. Thank you, first of all, Dmitry, for your wonderful review. I think you did a very nice job to summarize all these interesting results. One tendency which I think you did not include in your review is that we're actually trying to make models now which also try to fit the SED and other continuum observations. So we actually try to merge the kind of SED fitting dust modeling community with the chemistry and trying to fit the lines. So I think this is not only what we do, but also I see that this tendency also in other groups. This is quickly advancing, and I think it has some really interesting advantages because, for example, if you know a little bit more about the dust shape and a little bit more maybe about the sizes of your grains, about the dust opacity, it can actually change your chemical results as well. Yes. So my question is, did you look into this as well, and how would you comment on the role of, say, the disk shape and the opacities?
Thanks, Peter, for a nice question. Yes. Yeah, I completely agree that it's important also to model the dust emission or SEDs along with the molecular line data. For example, if you are looking at a disk that has an inner hole, apparently it may have a different temperature structure, but from SEDs, this is usually easily seen that there's, for example, dust which is very close to the star. We made a study, actually Stefan made a study of the grain size properties as a function of disk radius and a sample of disks in Taurus, where they also discern the radial variance of the grain properties and how they changed in different systems. So in principle, people do study that, and we also looked into that. And I agree that it will impact chemistry quite substantially, yes.
We just have a few more minutes, so I would ask the questioners to try to keep their questions short and also the answers as well. Leonardo.
Okay. Is this working? Yes. Okay. Leonardo Testi from ISO. Thank you very much for a great talk. I have a very specific question on this cold molecular gas that you mentioned. Actually, I was under the impression that in the new Alma observation of HD 16293, the molecule is actually higher in the layer than what we were originally thought. So in that case, is it the same? That how you see this in terms of the temperature?
You know, this HD 163296 is a Herbe-KE disk, so it's of course warmer than dm tau, and we don't see the evidence for cold gases in such systems. So I think there is no contradiction. On the other hand, it's not that hot to prevent a complete CO freeze-out. There is a CO freeze-out in this system, actually.
Question up on the balcony, please.
Yeah, here. From the water that exists in the planets, when the planets are already formed from the disk, what fraction of water is formed in the protoplanetary disk, and what fraction is already formed before the disk is formed? Thank you.
Yeah, you know, the current idea is that water forms mostly on the surface of dust grains and already in the pre-disk phase, more or less. It could even form before the formation of molecular cloud, you know, or during the formation of the molecular cloud. Whenever the dust is able to cool off before, let's say, below 100 Kelvin, a bit lower, then atomic oxygen can start to stick, and at some point the hydrogen atom will be able to stick as well, and then the water is formed. And then it only reprocessed during the formation. So you first assemble the dense core, then it starts collapsing and form a disk. And then, of course, you have heating events that may desorb some of this water, maybe even destroy it. And then when it cools off, the water vapor then freezes out. But the pristine water possibly most likely comes from the pre-disk phase.
Hans, quick question.
Okay. You referred to the detection of HD by Ted Bergen with Herschel, and you kind of were we're not sure how this will continue after Herschel died, but I have to remind you that there is Sophia.
Yes.
And,
actually, I forgot
and
about
actually, I have to tell you that Sophia just took off an hour ago in New Zealand. And during this campaign in New Zealand, we're actually going to try to find the HD if it works. So stay tuned. And I also would like to remind you, come to our booth.
Okay,
Sophia
great.
booth.
Thank you.
And
Thank you.
last question, Ruud.
Ruud Visser, University of Michigan. Just one quick comment to the question from upstairs. We have run models a few years ago that show that the water that is formed before it enters the disk, most of that actually survives going into the disk. So that's just a quick comment. A question on the cold CO and the cold other molecules below their evaporation temperature. There have been two suggestions in the literature that this could be non-thermal desorption, photodesorption, or that this could be due to turbulence where you would be mixing the cold gas up to where you observe it and it doesn't freeze out yet. Could you comment on which one of those two scenarios is more likely?
Yes, I mean, I did, my first incentive to do the mixing studies was exactly to try to explain these cold gases, but my feeling is that it's a bit controversial. Yes, for some molecules you do transport gases from the molecular layers to the cold midplane, but for CO it doesn't really work. I mean, more plausible hypothesis could be, the grain evolution, that you have predominantly large grains that sedimented to the midplane that delays the freeze out, and so that you have less possibility for the molecules to stick, so they tend to remain in the midplane. On the other hand, you still have to have enough layer of small dust at top to prevent this midplane to be heated up directly. So, but I guess the grain evolution could be more related to that. Yeah.
Let's thank our speaker again. Thanks, Dmitry.